Hello everyone, my name is Benedicto Frank. I come from the Barcelona Supercomputing Center, and today I will present you pyLOM, a high-performance computing suite of code for model order reduction. Actually, this is joint work that we have been doing together with Arnau Miró, Yvette Rodriguez, Nathan Kutz, and Uriol Lemkul. And as I was saying, pyLOM is a high-performance computing suite of code that we are using for reduced order models and that we have been developing at the Barcelona Supercomputing Center together with the Universidad Politécnica de Madrid. The main goal of pyLOM is being capable of performing reduced order models of large-scale computational fluid dynamics, like the two videos I have here next to me. The first one is the wall model LES simulation of an aircraft, and the second one is the wall resolve simulation of the flow around the car. In both cases, the grid is close to 1 billion grid points, and we need to collect more than 1,000 snapshots to be able to get all the information that we want from the flow. So we need, of course, this. If we want to do a reduced order model of that, we actually need a high-performance computing code that allows us to do it. And in this case, we developed pyLOM. In pyLOM, we have several reduced order modeling methods, from which I would like to highlight the dynamic mode decomposition, proper orthogonal decomposition, and spectral proper orthogonal decomposition, because we have achieved a highly parallelism with it, thanks to some algorithms that I will describe here in this video. But in pyLOM, we don't only have the algorithms to do the decompositions in parallel, we also give support to a parallel input-output of the data so that we can actually exchange with different formats, and also that we can visualize it, for instance, using ParaView. Apart from that, we have a parallel package for mathematical operations that it can be either done using Python or with compiled C in the backend. Although pyLOM is a Python package, as its name clearly shows, the user may compile it to be able to use a back-end C operations when performing their decompositions. So let's take a deeper look on the key of pyLOM when being so efficient when computing the proper orthogonal decomposition, DMD, and also the SPOD. That is the parallel singular value decomposition of pyLOM. Parallel SVD of pyLOM actually just gets the flow data or any data that the user may want to have and appends the each snapshot of the data in a different column of the matrix. So in the end, we have our snapshot matrix, that is a matrix A, in which every column represents a snapshot and every row represents a grid point. So, as I was saying at the beginning, for the cases that pyLOM has been designed, we have billions of grid points, but only thousands of snapshots. So matrix A is tall and skinny, and we parallelize it by dividing the rows that we have in the different ranks that we have available. Instead of doing the SVD straight away, in pyLOM we use a well-known analogy in linear algebra that basically says that performing the singular value decomposition is cheaper if first one performs the QR factorization. So we obtain the Q matrix and an upper triangular matrix R of our data, and then we perform the singular value decomposition just in the upper triangular matrix R, which of course is much cheaper than doing it on the full dataset. The results of the SVD on the R matrix are actually equivalent to the ones of the original dataset. This is especially true for the singular values and the right singular vectors, which are straight away the ones of our original data. If we want to recover the left singular vectors of the data, we just need to multiply the ones obtained from the matrix R with the Q matrix that we have obtained before. So the problem of computing the parallel singular value decomposition now becomes a problem of performing a parallel QR factorization. If we continue with the example that we had at the beginning, that basically was the matrix A split in 4 different ranks, we can see how to actually build this parallel QR factorization. So this QR factorization first starts with the local QR factorization of the data in every rank. So every rank gets a chunk of Q and a different R. Now it's a matter of communicating all this data through all the ranks so that we can get the same information on every rank, and every rank gets a factorization being aware of the data of the full matrix. To do so, we follow a binary tree reduction algorithm In that way, we avoid that all ranks try to communicate with the rest at the same time. That's what would happen if we were using an all-gather reduction process. So with our binary tree reduction algorithm, we have several levels of communications. The more ranks we need to communicate, the more levels we're going to have. And in each of the levels, each rank only communicates with a pair, with one colleague, let's say, okay? So for instance, here, rank 1 and rank 0 are colleagues, so rank 1 sends its information to rank 0. They only send the R matrix. There's no need to send the initial Q matrix, which actually saves a lot in terms of communications. And then the rank 3 and rank 2 are colleagues again, so here, rank 3 sends information to rank 2. Then rank 0 and rank 2 that have received the information from their colleagues perform the QR of the concatenated R matrices and get an updated Q, an updated R. And at the next level, as we want to reduce everything to one rank, so that we are aware of what's happening to the rest, rank 2 and rank 0 are colleagues now because they are the only ones with new information, and rank 2 just shares it with rank 0. Rank 0 will perform the QR on that new information, and we'll have a matrix Q that will contain the information of all the data, and a matrix R that will also contain the information of all the data. So at this point, rank 0 will broadcast the data on a similar broadcasting algorithm to the rest of ranks so that everyone knows actually what was going on. If you want to know more about this algorithm and its performance, we have a paper published talking about how this is implemented in pyLOM and how this is key to the performance of pyLOM. I actually give you, here you will have the link of the paper, which I recommend you to read to fully understand it better and to be able to see how this helps the performance and to know a bit more on the performance bounds of pyLOM. But if you want just to use it, I will just quickly tell you how to deploy pyLOM, which is quite easy. It's as easy as doing pip install pyLOM order, and you will get pyLOM version running on your laptop or your HPC cluster that runs on CPUs and in parallel. If you don't have many CPUs and you would like to just use GPUs, we have also this algorithm implemented in parallel for GPUs. In that case, you just need to add this CUDA 12x at the end. So we are going to have pip install pyLOM order CUDA 12x to use the GPU version of pyLOM. And if you want more performance, I was mentioning at the beginning of the video that you might want to compile the source code so that you get CPU extra performance using compiled C code for the mathematical operations instead of using just the Python libraries at the backend. So if that's the case, you just need to go to our GitHub repo or to our wiki. I don't know if I mentioned that, but pyLOM is fully open. So we just can click here, find our GitHub repo, the wiki of pyLOM, and just go to the installation guide. Here you will have all the instructions on how to compile that on your cluster. We actually recommend that option if you are thinking on using pyLOM on a large CPU HPC cluster because you're going to find massive performance with a compilation. If your cluster is GPU based or you just want a simple installation just to try, just go with the pip install option. And then how do you call this algorithm in pyLOM? What do you need to do? Well, imagine you just want to do proper orthogonal decomposition. So doing that in pyLOM, it's as simple as doing pylom.pod.run and input to the function the matrix that you want to decompose. Of course, the matrix, as you're running in parallel, you will need to make sure that every processor has a chunk of this matrix and it's split row-wise, but for the rest, it's just as easy as calling pylom.pod.run. Our POD function has several options like removing the bin beforehand. Also, if you want to perform randomized POD, from which I will talk after in this video, and in case you want to do randomized POD, how many modes do you want to retrieve and how many power iterations do you want to do. If you want to know a bit more how to do POD and a bit more examples on how to do that, we have a notebook example in our wiki on how to do parallel proportional decomposition, and we have several scripts of examples that are in our GitHub repo. I actually give you also here the link to the examples. So let me show you what can you do with pyLOM and 3,584 CPUs. So we got 4 different meshes of 4 different cases that we had. The smallest one was 50 million grid points, up to the billion grid points that I was talking at the beginning of the video. And then for these meshes, we used several number of snapshots, okay, from 100 to 1500 snapshots. And we perform POD, the QR factorization actually, using the different number of processors up to these 3,584 CPUs. So we got this plot, and in the x-axis, okay, so here we have the local load, so how many rows each processor has, and on the y-axis we have the time that it took to perform the factorizations. So when you go to the right on the x-axis, actually means that you are using larger meshes. When you go to the left on the x-axis, it means that you have more CPUs, so you have less load per processor. And of course, when you increase the number of snapshots, it also increases the time. So you will typically see that the higher you go on the y-axis, it means that you are using more snapshots. What is interesting to see from this plot is that we have this combination of different meshes and different snapshots. So we can see with this amount of CPUs, which is the larger matrix that we can decompose. So if we were thinking about a billion matrix, a billion grid points matrix, we see that the maximum mesh that we could decompose was the one with 100 snapshots. And the one with half a billion was about 1000 snapshots. So this is something that we can tackle when performing the randomized factorization. We will cover it in the future slides of this video. Also, before moving into the randomized, I just said that you could actually decompose quite large matrices when using, a lot of CPUs, no? Like we were talking about 3000 CPUs, which is quite a lot of CPUs. But you can also have, let's say, cheaper parallel singular value composition, especially if you have GPUs, that it's something much more affordable in terms of buying the hardware and energy and maintenance for, to just have it in a small workstation or a small cluster. So we actually have access to a cluster with 10 GPUs of NVIDIA A6000 and in that cluster we could factorize a matrix with 80 million grid points and 250 snapshots with only 2.71 seconds. Okay, just for reference, the cost of this cluster is around 55,000 euros, which is much cheaper than having that many amount of CPUs. So now also here we were constrained to these 250 snapshots. Before I was talking that if we wanted to go to the billion grid points mesh with the amount of CPUs that we had available, we could only do 100 snapshots or maybe something more, but we couldn't reach the 500 snapshots. So how can we solve this issue? How can we go to more snapshots when we are constrained on our computational resources? Well, we do that with the randomization of our data. So we have an algorithm that allows us to do parallel randomized QR. This parallel randomized QR basically is based on, as any randomized factorization, randomizing our data so that we can reduce the number of columns that it has, but we still conserve all the dominant features in the data. Okay. So when we do that, we obtain a much thinner matrix called Y, that is the one that we are going to perform the QR factorization from. This QR factorization is much cheaper because we have less columns to factorize, but still those columns have the optimal information that we could find. So this is quite an interesting algorithm. And once we just have this factorization, well, now we need to find the correct R in that case, which we're going to name B because it's not anymore an upper triangular matrix. And this B matrix, it's just a projection of our data matrix A to this Q that we have found through randomization. You have to note here that, well, as both A and Q are splitted in different processors, this matrix-matrix product has to be done in parallel. So to do that matrix-matrix product in parallel, first of all, each of the processors, it's going to multiply the chunk of the data that they have, and after that, we are going to do an all-reduce operation in all the processors to sum this data. Okay, this assumption of having the same splitting on the on both matrices that are being multiplied allows us to do this simple algorithm for the matrix-matrix multiplication, and we can obtain this B matrix in that way. So the parallel product of each of the chunk of the data, and then just the all reduce and summation of them. But what if we actually now have a massive amount of snapshots? So we have a matrix that it's not tall and skinny anymore. So we need to do some kind of streaming and parallel QR, because we need to load our data in chunks and then perform the QR, remove our data because we cannot store it. It's so big that we couldn't store it all. Then load another chunk of data, update our QR results, and so on, like with as many snapshots as we want. So how can we do that? Of course, the first step would be randomizing. No, like actually we have to see this problem as if we're performing the randomized factorization of a very large matrix. The only issue extra that we have is that we cannot fit it in memory altogether. So what we're going to do that is loading that by chunks, and we can just do this factorization by chunks. Well, just by the properties of matrix products, this matrix of A times omega, to find Y, if we do it in chunks, basically we see that the final Y is actually the sum of the result of the product of every chunk. Okay, so this step of finding Y is actually quite straightforward. It's just multiplying each of the chunks of A by its corresponding chunk of omega and adding them all together. So let's do that. Okay, let's get the data of the first chunk. We get this Y0, which is the randomized first chunk of data. We perform QR of that chunk, okay, and we have our first Q columns of the data. Once we have it, we just project our first chunk of data to the B of this chunk of data with a parallel matrix product that we saw some minutes before, and we can discard our matrix A of that chunk. Now we go to the next chunk of data. So now you realize that, well, our Y is not a new Y. We want that this Y already takes into account the previous information that we had. So by the matrix product properties that we saw before, we can just add the new randomization to the previous Y that we have and perform QR of this Y. Now the new Q that we obtain is a Q that its columns have information of the first chunk of the data that we already eliminated and the new chunk of data that we are trying to factorize right now. So we have a different Q, and now we need to find a new B. So this update of the B has two different steps. So first step, we call it that we compute B plus 0. So let's say it's the update of the previous B that we had, okay? So we need to update B0, considering that now our Q is not Q0 anymore, it's Q0 and 1, because we have information of a new chunk of data. And then we need to compute the new B, okay, the B1, which is just a projection, okay? That step is what we saw before. It's just the same as we have seen before, and we are going to just concatenate both of matrices, okay? But how do we do this update? The easiest thing in terms of algorithm would be just being able to project the chunk of data that we have eliminated again with this new Q. So in that way we could do this update. But as I said, our data is so big that we have first eliminated it, and second, we couldn't afford of just doing an iterative loop of uploading a new chunk of data every time that we want to update the new B. So how do we do that? We reconstruct the previous chunk of data that we have with the previous Q, okay, with Q0 and B0, that is the one that we want to update. So in the end, it's just doing the projection of the product of Q0, B0 to the new Q. So to perform that product, considering that B0 actually in the next iteration it's going to be B01, then it's going to be B012, so it's going to grow a lot in terms of amount of snapshots that we have. So what we're going to do first is always this parallel matrix product. In that way, we are actually constraining the size of our product a lot. We remove all the large scale computations. We are removing all that with a parallel matrix product that doesn't increase in size when we have more snapshots to update. That's important because that makes our algorithm that stable in terms of iteration cost when we grow the number of snapshots. So once we have that, we can just continue that process indefinitely because we know that it's not going to grow. And that actually leads us to a really nice pathway to a billionaire singular value composition, because now, well, we had our dataset with 1 billion grid points that was constrained to less than 500 snapshots when working with 3,584 CPUs. But with the streamwise randomized QR from pyLOM, we can load more snapshots, okay, into that, and without worrying about having to add more computational resources for the factorization. To do that, we just gathered the 190 most relevant modes of chunks of 200 snapshots with the algorithm that I just explained recently. And with that, we had that each update took 17.1 seconds. So that process can actually be extended indefinitely in time without an increase of the cost per update. So the only constraint that we have here is, of course, that our system, the modes of our system, are more or less steady and they don't have a strong divergence point during our updates, which is something that happens in the cases that I've been showing at the beginning of this video, and in the cases that we are targeting with pyLOM. So that's actually the end. I want you to keep in mind that we are in that pathway for the billionaire SVD. That's actually what you can do with pyLOM, getting to a billionaire singular value composition. And if you just want to use pyLOM, just remember to take a look to the links that you have here with the GitHub repo, the papers of pyLOM, and also the wiki of pyLOM. And that if you want to try it, it's just as simple as using pip install pyloorder or pip install pyloorder CUDA12x if you have a GPU cluster, because apart from having good scalability on CPU, we also have good scalability on GPU. So that's the end of my video. Try to use pyLOM. I do encourage you to use it for any dataset that you have, and I hope that you enjoy while you use it.